and submerged bodies. In some problems, we maybe have, let me write a equilibrium of a fluid element. The pressure gradient is a surface force that acts on the size of element. There may also be body force due to electromagnetic or gravitational potentials acting on the entire mass of the element. Here we consider only the gravity force or weight of the element. So we can write the gravity force dF equals to m, which is rho, multiplied to b dx dy dz. This is the element volume multiplied to g, equals to rho g dz. In addition to gravity, a fluid in motion will have surface forces due to the viscous stresses. By the Newton's second law, the sum of these per unit volume forces equals to the mass per unit volume times the acceleration a of the fluid elements. So we have from Newton's law that ma, in this case we have three forces: F, pressure, gravity, and viscosity. Equals to the gravity force. The pressure force we calculated before is the gradient of the pressure, and the gravitational force is rho g plus F is going to multiply to m r rho r. In this case, we can write F gravity equals to rho g, and F is dF on dB. Net force on the element. So we have three expressions in right hand side and one expression in left hand side, and right hand we have one expression. This general equation will be studied in detail in chapter 4. Note that this equation is a vector relation and the acceleration may not be in same vector direction as the velocity. For our present topics, hydrostatics, the viscous stress and the acceleration are 0. So in the hydrostatics we write in this chapter, in the hydrostatic problem, F viscous equals to 0, R equals to 0, and we have the expression only for minus equals to 0. The description of this equation will be discussed later. Gauge pressure and vacuum pressure relative terms. In the next page. Gauge pressure and vacuum pressure. Before embarking on example, we should note that engineers are apt to specify pressure as the absolute or total magnitude. So two types of pressure we may have: one absolute pressure, the value relative to the total ambient and relative pressure to ambient. The second case occurs because many pressure instruments are of differential type of records, not an absolute magnitude, but the difference between the fluid pressure and the atmosphere. The measured pressure may be either higher or lower than the local atmosphere pressure, and each case is given a name. For example, in gauge pressure, if P is greater than P atmosphere, we have gauge pressure. In this case, P gauge equals to P minus PA. This is the second relation is if P smaller than PA, we have vacuum pressure where P vacuum equals to PA minus P. This is a convenient shorthand, and one letter adds or subtracts atmosphere pressure to determine the absolute fluid pressure. A typical situation is shown in this picture. The local atmosphere is at say in this point, local temperature, local atmosphere point. The higher pressure categorized as the gauge pressure, and the lower pressure classified in the vacuum pressure as this point. So vacuum pressure, we have the local pressure P is equals to 90,000, and vacuum pressure equals to 50,000 Pascal, and also P gauge equals to, in this case we can write P vacuum equals to PA minus P, which is in this case we have PA here, 90 minus 50 equals to 40,000 right here also, and in this case P minus PR equals to, we have equals to, as its price, 30,000 Pascal gauge. Next description in this chapter, hydrostatic pressure distribution. Let me write hydrostatic pressure. Hydrostatic pressure distribution. If the fluid is at rest or at constant velocity, A equals to 0, and the force due to viscosity also is to 0. So as we said before, if the fluid is at rest or at constant velocity, then A equals to 0 and F viscous equals to 0. So the equation as before, we have 3 minus rho G plus F rho A. In this case, we can write as a result these are 0 and also gradient of the pressure equals to rho G, the equation, and in the vector form we can write the gradient form of pressure and the gradient form of G. This is a hydrostatic distribution and is correct for all fluid at rest regardless of their viscosity, because the viscous term vanishes identically. The Coulomb vector analyzes that the vector gradient P equals to expresses the magnitude and direction of the maximum spatial rate of increase of the scalar property P. As a result, the gradient of P is perpendicular everywhere to the surface of constant P. So this equation states that a fluid in hydrostatic equilibrium will align its constant pressure surface everywhere normal to the local gravity vector. The maximum pressure increase will be in the direction of gravity, that is down. If the fluid is a liquid, its free surface, being at the atmosphere pressure, will be the normal to the local gravity or horizontal. You probably knew all this before in the Part equation in hydrostatics as shown in this relation is the proof of it. In our customary coordinate system, Z is off, thus the local gravity vector for the small scale is G equals to minus G cup, where G is the magnitude of local gravity. For example, in the SI we have 9.81 m on second square, and we can write the vector form of the equilibrium condition for hydrostatics flow as below. Equals to so we can write and minus G minus rho G. That it is a specific weight, also we can write as this for the first two of which tell us that P is independent of x and y direction. Hence the rho P on rho Z in this expression can be replaced by the total derivation dP on dz equals to the, in the hydrostatics form we can write dP on dz equals to minus rho G equals to minus gamma specific weight. So we can write an integration for calculate the dp or dz. So we can write dp equals to minus dz. So integration from point 1 to point 2 delta z. This equation is the solution to the hydrostatic problems. The integration requires an assumption about density and gravity distribution. Gases and liquids are usually treated differently. We stated following conclusion about a hydrostatic condition. Pressure in a continuously distributed uniform state static fluid varies only with the vertical distance and is independent of the shape of container. So we can write the conclusion for this section. The pressure in continuously distributed uniform static flow, pressure in the in a usually distributed uniform static fluid varies only with vertical distance and is independent of the shape of the container. Is independent the shape of container. The pressure is the same at all points on air, so the pressure is same in all directions at all points. Let me write. On a given horizontal plane in the flow. The pressure increases with the depth in the fluid. Increases with the depth in the fluid. Effect of variable gravity also described in the dynamic and static courses, also in an spherical atmosphere. Let me write the effect of variable gravity. For a spherical planet of uniform density, the acceleration of gravity varies inversely as the square of the radius from its center. And we had this g equals to g0 R0 on R square, where R0 is the planet radius, R and G0 is the surface value of G, there is a some magnitude of R0 and the R0 equals in the references such as kilometers, or R0 equals to 3,960 miles. In the typical engineering problem, the deviation from R0 extends from the deepest oceans about to 11 kilometers to the atmosphere height of the supersonic transport operation about 20 kilometers. This is a maximum variation in G equals to about 6-10%. We therefore neglected the variation of G in the mass problem in this course, fluid mechanics, hydrostatic pressure in liquids. So we have another definition. Hydrostatic pressure in fluid. Liquids are so nearly incompressible that we can neglect the density variation in hydrostatics. In example, we can write the water density increase only by the, for example, large pressure only 4%. For example, its effects on hydrostatics would be about half of this percent. For example, in the comparison about 100 atm. This was assumed of constant density in liquid hydrostatics calculation, the previous hydrostatics equation, which was delta gradient of P equals to rho G, and in the Z direction we had dP on dZ equals to minus gamma. In the case of the fluids, gamma is rho is constant and G also is constant, so we can write dP equals to dZ. So delta P equals to minus dZ. We can write between 2 points minus gamma, this relation for the hydrostatic pressure, so the minus Z1 equals to P2 on P1 on gamma minus P2 on gamma. Gamma is the specific weight. A specific weight on various fluids such as air, ethyl alcohols, oil, water, seawater, glycerin, carbon, tetrachloride, and mercury is available in the reference black and white chapter 2 table. We use this equation to, in most problems, the quantity gamma is called the specific weight of the fluid with dimension of weight per unit volume. Some values are tabulated in the tables. The quantity P on gamma is then called the pressure load of the fluid. So if we equated with the pressure load of the fluid, it means that fluid is P on gamma. Pressure load of fluid. The next description for the related to this chapter is the application of hydrostatics equation, the Mercury barometers. The simplest practical application of the hydrostatic formula is the barometer as shown in this picture. Let me write the hydrostatic formula, which was minus gamma delta Z, or the in the gradient form we can write the minus gamma, and in the hydrostatics form we have this relation for the hydrostatic pressure, and application of the hydrostatic pressure is Mercury barometers. Consider this picture for Mercury barometer description. This figure is the barometer which measures atmospheric pressure. The tube is filled with the mercury and inverted while submerged in a reservoir as shown in this picture. Mercury reservoir and tube. This causes a near vacuum in the closed upper, and because mercury has an extremely small vapor pressure at room temperature, since atmospheric pressure forces a mercury column to rise a distance h as shown in this picture here, we can obtain a relation between the pressure and the mercury displacement in the tube. So in the formula of equation applies, we can write the relation. We had this relation for the P2 minus P1 on minus gamma equals to Z2 minus Z1. We need to select a datum. In this case, Z2 is the datum. Z2 equals to 0, Z1 equals to H. So we need the appropriate pressure for each Z. In the Z2 we have P equals to PA, and in Z equals to 1, Z1H, P equals to as we said, mercury has a very low vapor pressure, P equals to 0, equals to P2 equals to P1. So with displacement we have this relation PA minus 0 on minus gamma equals to Z2H minus 0. So we can write H equals to PA on H. In this case, we should write the 0 minus h. 0 minus h. So we have also a correction here, P on gamma mercury. So if we had h, we can calculate PA. PA equals to gamma h, the pressure of the atmospheric pressure. Atmosphere pressure. With the hydrostatic equation, we can calculate the atmosphere pressure with mercury, because the vapor pressure is near 0 in mercury. We can also use other fluids, but we should determine first the vapor pressure of that fluid. The next video is our description about hydrostatic pressure in gases and other section in the chapter 2.